Hello. After discussing the classical theory of diamagnetism, we will discuss the quantum theory of diamagnetism. And we will do that for mononuclear systems. That means there is one nucleus in one unit cell. So the effect of magnetic field will add some terms in the Hamiltonian. Let's write down those terms. So I am not writing the full Hamiltonian, I am just writing the terms that are added to the Hamiltonian as a result of the application of an external magnetic field. That is given as I E H cross over twice m c. C is the velocity of light, del dot the vector potential plus the vector potential dot del, this operator, plus the second term is E squared over twice m c squared, the vector potential squared. Now, if we consider an atomic electron, these terms may usually be treated as small perturbations. These are much smaller than the other terms of the Hamiltonian. And if the magnetic field is uniform and it points along the z direction, then we can express the vector potential in the following way. Ax, that is x component of the vector potential, would be half yb, b is the magnetic field pointing along the z direction, ay is given as half xb, and az will be 0. And with this, the Hamiltonian that we wrote earlier can be expressed as I E H cross times B, the magnitude of the magnetic field, over twice m c x d dy minus y d dx plus E squared b squared over 8 m c squared x squared plus y squared. Now, the first term here, that is this term, is proportional to the orbital angular momentum component L2 if r is measured from the nucleus. In mononuclear system, this term will give rise only to paramagnetism, and the second term, this one here, that gives for spherically symmetric system a contribution in energy E prime equals E squared b squared over 12 m c squared r square expectation value. This is obtained by first order perturbation theory from this second term here. And the associated magnetic moment is diamagnetic for this second term, where mu is given as minus del E prime del B. which is, if we work it out, minus E squared R square average over 6 mc squared times B, and this is in agreement with the classical result. So, we have got the magnetic moment that comes from the quantum theory of diamagnetism.